Welcome to the course of Wireless Sensor Network. I am Dr. Zishan Bangash, Assistant Professor, Institute of Computing, Cohort University of Science and Technology. And today we will be talking about sensor network programming. This is lecture number 7. So let's discuss the outline of today's topic. Since application development for sensor networks differ in many ways from the traditional distributed systems, so from the network developer's perspective, the goal is to design and program a reliable and efficient wireless sensor network that can cope with the dynamic and uncertainties present in the sensing system. And from the user perspective, the network is often viewed as a database, and the users interact with sensor nodes via queries, which may be responded in a reliable and effective way. So, there are many simulation tools and techniques that are closely tied with the operating system that are used for sensor node programming. So, we will be discussing some challenges that are involved in programming a node, and then a specific technique, that is node-centric programming, keeping in view the language platform, that is the NESC is the language that is mostly used for programming a node, and the operating system, that is TinyOS is the operating system used in most of the sensors. And we will be discussing a sample piece of code uh, that is written in NESC, and at the end we will summarize our today's discussion. Wireless sensor networks are a special type of network, and the different characteristics of this type of network makes this type of network very challenging to be programmed. Uh, we are not talking about programming some hundred of devices that are split across a network. We are talking about a type of network where thousands of devices that are uh, deployed at a remote location, that have very limited computation power, that have very limited storage capacity, and that are that have a very limited battery power. So the programming platform or the programming model should consider these constraints. We are not going to develop an application that involves heavy computation. It should be lightweighted and intelligent, and similarly the model should be adopted so that when any communication from a central point to these nodes for any phenomena to be observed is taken place, so that should be communications needs to be processed in a very lightweighted way. The overall congestion in the traffic of the networks needs to be controlled. So these are different challenges. The topological changes, and particularly the changes in the in the dynamics of this network is of key importance. So these are a few important things about programming a wireless sensor network that must be keep into consideration. So let's discuss some of the challenges in detail. Wireless sensor network is a special type of network that involves many constraints. It's a type of network where most of the sensors that are in thousands are deployed at an unintended environment in order to observe any phenomena, and they continuously report to the central point, that is the sync node, in the form of some data, some signals. So, in order to program such a distributed system, some of the main challenges involves the reliability constraint for this type of network, the resource constraint, the scalability constraint, and the data centric networks constraint. So let's discuss the first constraint, that is the reliability constraint. Wireless sensor networks are actually unreliable than any other distributed systems. Therefore, sensor networks are built to adapt to changes dynamics and nodes and the errors such that the network continues to serve its purpose even when the whole or part of the network have failed. While many faults in such a network will never be noticed by an application, however, such type of networks needs to be resilient to the failures, and the topology changes frequently. So this change in the topology needs to be supported by the programming environment. So this is regarding the first challenge, that's about the reliability constraint. The second challenge is the resource constraint challenge. WSNs are very resource constrained, which also affects the programming approach, the size of the code to be written, and the other aspects of the application that is to be developed. So, energy efficiency is particularly of critical importance in WSNs, and it penetrates in every aspect of sensor network design, whether it's from duty cycle to routing protocols or to in network data processing. So, this energy efficiency is crucial for every aspect of the application design. Therefore, programming tools and the programming models should allow a developer to effectively exploit energy saving techniques and approaches, and at the same time the details needs to be hidden from the programmer. The third constraint is the scalability constraint, and sensor networks can scale up to hundred and thousands of sensor nodes. So therefore, the programming models should support developers in designing application and softwares for such a large type of network. Many configuration, maintenance, and repair of individual sensor node will be infeasible due to the large number of the devices. Therefore, there is always need for self management and self configuration, as this is a sort of unattended network. The scale of this network can be addressed by using programming models that can consider the entire network as one whole entity instead of focusing on an individual device or a particular node. The fourth important challenge to be discussed is data centric network constraint. In many sensor networks, not only the individual sensor nodes are of interest, but also the data they generate and disseminate, that is equally important. Sensor network applications are therefore concerned about obtaining useful information in a timely fashion, which where it is irrelevant which sensor node generate this information. So that needs to be keep in consideration. So this is a special type of again that network, and you can just see that the different devices or signals that are present at different locality, they are transmitting their data or observing the phenomena through the wireless medium to a central part, which is a sync node. So the challenges that are involved uh, may vary from application to application. However, the four challenges that have been discussed are particularly of key importance when we program a node. So we discussed about the reliability constraint, and we talked that the resilience to changes and failures is important in WSNs, and they should be supposed to be supported by the programming environment. We talked about the resource constraint, that the resources are very limited, and there are limitation on the maximum code size, and similarly the performance also varies because of the shortage of the or the limited storage and the battery constraints. uh, Also, the programming environment needs to allow programmer to exploit energy saving technique, so this is another challenge. We talked about the scalability, that's sensor networks can be very large, and programming model must be scaled, and we talked about the manual configuration that is not possible, and there's need for unattended network management, and since the repair is infeasible. And we talked about the data centric networks, that in this type of network, the concentration on the devices are not important, but the main focus is on the data. So let's discuss the specific programming technique for programming a node, which is node centric programming uh, under the node centric model. What is this node centric programming? It's basically the programming abstraction um, that is under the node centric model. It's a programming abstraction, and the languages and the tools that are focused on development of sensor softwares on a per node level. The overall network wide sensing application is described as a collection of pairwise interaction of individual sensor nodes. The programming language for programming a sensor is NESC, which is an extension to the popular C programming language, and it provides a set of uh, language constraints to implement code for distributed embedded systems, such as modes. Unlike traditional programming languages, NESC must address the unique challenge of WSN. For example, activities in sensor networks are initiated by events such as detection of change in the physical environment. These events may occur while a node is processing data. That is, sensor node must be able to concurrently perform their performance task while responding to the event. So the whole programming model comprise of the NESC programming language along with the tiny operating system considerations. And sensor networks are typically, or the sensor nodes are typically very resource constrained and are prone to hardware failure. Therefore, programming language for sensor nodes should take these characteristics into consideration. And as already we have discussed that it's basically the extension of popular C language. Now, the application of based on NSC consists of collection of components, and each component has a provides and uses interface, where where a provide interface in NSC is a set of method calls that are exposed to higher layers, whereas the uses interface is a set of method calls that hide details of lower layer components. An interface describes the use of some kind of services, for example, sending a message. So let's discuss a simple example code. This example shows the definition of for the timer, STD control, clock, send, and the sensor interface. The timer interface defines two types of commands that are start and stop. The timer interface further defines an event, which is also a function, while the commands are implemented by the providers of an interface. Events are implemented by the users. And similarly, all the interfaces that are shown in these examples define both commands and events. Apart from interface specification in NSC, NSC also have implementation. So the modules are components implemented by the application code, while configurations are components that are implemented by connecting interface of existing components. Every NSC application has a top level configuration that describes how components are wired together. Functions in NSC are described as f.I. You can just see on this slide that in f.I, f is a function in an interface I. So the functions are invoked using the call operations and the signal operations. So the code shown in the next slide is implementation of an application that periodically obtains sensor readings. In the upcoming piece of code, the std control.init is called at a boot time, and it creates a timer that expires after every 1000 milliseconds, and upon the time expiry a new sensor sample is obtained. So this adc.getData, it triggers sensor data acquisition. So in this example, this, as already stated, that the std control init is called at boot time, and that and the timer expires after a particular time, and a new sensor sample is obtained by adc.getData, which triggers the actual sensor data acquisition. In TinyOS, code executes either asynchronously, that is in response to an interrupt, or synchronously as a scheduled task. So the race condition can occur when concurrent updates to shared states are performed. In NSC, code that is reachable from at least one interrupt handler is called asynchronous code. and a code that is only reachable from tasks is called synchronous code. So the asynchronous code is reachable from at least one interrupt handle, whereas the synchronous code, NESC code, that is reachable only from tasks. So the synchronous code is always atomic to other synchronous codes, and it's always executed sequentially and without any preemption. So the race conditions occur when there is concurrent updates to share states and performed. Synchronous code is always atomic to the other synchronous code. However, the shared state is modified from AC, or when shared state is modified from synchronous code, that is also modified from asynchronous code. Therefore, NESC provide programming with two options to ensure atomicity. As already discussed, the first option is to convert all the sharing code to tasks, that is to synchronous codes only, and the second option is to use atomic sections to modify the shared state. Atomic sections are indicated with the atomic keyword, which indicates that block of statements should be executed atomically, that is without preemption. So we discussed that the NESC provides two options for ensuring atomicity. As you can just look into the code shown on this slide. Then there is no preemption that can be obtained by disabling interrupts during atomic sections. So in today's discussion, we talked about some of the challenges of wireless sensor network, that includes reliability constraint, the resource constraint, the scalability constraint, and the node-centric programming constraint for programming this special type of network. Then we discussed about the node-centric under the node-centric model. That's the programming, which is basically a programming abstraction, and it focuses on the development of sensor softwares on a per node level. We discussed the programming language NESC, which is an extension of C language, and that provides set of language constructs to implement code for distributed embedded systems like modes. And we discussed that these sensor nodes are resource constraint and are very much prone to hardware failure. We discussed some piece of code, and we talked about that in TinyOS code execute either asynchronously or synchronously, and race conditions can occur when concurrent updates to share states are performed. So this is our today's discussion about the sensor network programming part 1, and we will be discussing we will be discussing more details in the upcoming lectures. So these are some of the references from which the content has been taken and prepared, and thank you very much for watching this lecture, and do subscribe our official media server channel at ms.cohort.edu.pk. Thank you. Take care. Allah Hafiz.